Hello children, welcome back to the channel. Today we will be discussing about the variation of acceleration due to gravity with different factors. That is to say, we already have discussed about an expression for acceleration due to gravity in the previous video, where we have found that g is given by gm by r squared. Not r squared, capital R, small r squared. Okay, and also we know that force of gravitational attraction F is gmm by r squared, where m is the mass of the object and r is the distance of the center of the object from the center of the earth. Okay, now first let us consider the variation of acceleration due to gravity outside the earth's surface. That is to say, if the object is on or above the earth's surface, how the acceleration due to gravity will vary. Okay, so with altitude, that is with height from earth's surface, how acceleration due to gravity is going to vary. Now, first and foremost, we already know that when the object will be at earth's surface, acceleration due to gravity, as we have discussed in the previous previous video, we know that g will be given by that is at point A, which is on the earth's surface of the earth. If this is the earth, m is the mass of the earth and r is radius of earth, then at point A on the surface of earth, g will be given by gm by capital R squared, as we have found in the previous video. If you haven't seen that video, link will be given in the description. You can always refer to that video. Okay, now if I say point B, which is at a height altitude of h above the earth's surface, then acceleration due to gravity at this height will be, as we have seen in the previous video again, will be given by gm by this entire height from the center. That is to say, the height or distance of the point B from the center of the earth, which clearly is radius of the earth plus the height or altitude of the object, which means gh will be r plus h, which we had said was r in the previous video. Okay, center to center distance. So r plus h whole squared, which means that acceleration due to gravity at a height with respect to acceleration due to gravity on the earth's surface will simply be gm by r plus h whole squared divided by gm by r squared, which will simply be r squared divided by r plus h whole squared. Or we can say this will be equal to 1 by 1 plus h by r whole squared. Right? Taking r common from here, so r square common from here, we have r square, and then this will be there, which can also be written as 1 plus h by r to the power minus 2. Okay, now we know that this kind of formula can be expanded. This can be expanded as an infinite series, which will be, the first term will be 1, then it will be minus 2h by r plus the other terms, higher order terms of h by r, that is h square by r square, h cube by r cube, and so on and so forth with the coefficients. Now if we consider that h is much less than r, which means the distance or height of the object with respect to from the earth's surface is not comparable with the radius of earth, or is very small compared with the radius of earth, then we can say that the higher order component terms, that is h square by r square or h by r whole square, will be a very small fraction, and so that can be neglected. So all the higher order terms of the infinite series expansion of this particular term can be neglected if we take h to be much less than r, that is the heights are much closer to the earth's surface. In that case, what we are left with 1 minus 2h by r, right? So we can say that acceleration due to gravity at a height must be equal to acceleration due to gravity on the Earth's surface multiplied by 1 minus 2h by r. Okay? So, since this term is, though it is small, it is not zero, which means at height h, the acceleration due to gravity will be less than the acceleration due to gravity at the Earth's surface. Now, this can be rewritten as g minus 2gh by r. Therefore, we can say that gh minus g, variation of g with height, that is, sorry, g h minus g, no, g minus g h. Why? Because gh is smaller than g. That will be a positive term, which will be 2gh by r. Now, since r is a constant, we have taken g and m are constant, so acceleration due to gravity on Earth's surface is a constant for the time being. Okay? Which means that g is constant, 2 is a constant, r is a constant, means that this term g minus gh will be proportional to h, the height. Okay. And if you are asked to find the percentage change in acceleration due to gravity, then it will be with height, then the acceleration due to gravity on Earth's surface minus acceleration due to gravity at height divided by acceleration due to gravity at the Earth's surface. This will give you the fractional change of acceleration due to gravity with height h. If I multiply this by 100%, we get the percentage change. Since this value is equal to this, so this will be equal to 2gh by r into 100%. Okay, now let's see how the acceleration due to gravity varies with depth below the Earth's surface. So let us say initially the object was at point A on the Earth's surface, Earth having a mass of m and radius of r. So g on the surface or point A will be gm by r squared. No problem about that. However, at this point B, the distance from the center of the Earth will become r minus d, right? Since point B is at a depth of d from the Earth's surface. So, from the shell theorem, we know that only the inner core or inner central part of the mass of the inner part of radius r minus d will matter. Let's say this mass of the inner part be m dash, which is less than m. In that case, g at this depth d will be g m dash by r minus d whole squared. Okay. Now, let's consider this. That density of Earth is constant and it is rho. Then clearly m will be equal to 4 by 3 pi r cube into rho, and m dash will be 4 by 3 pi r minus d whole cube into rho. Which means g can be written as 4 by 3 pi r cube by r squared, so it will be r rho into g. This will be there, right? And similarly, acceleration due to gravity at this depth will be given by 4 by 3 pi r minus d rho into g. Okay. Therefore, G at a depth d divided by G at surface will be the ratio of these two. So what we will be left with? 4 by 3, pi, rho and G, everything will cancel, so we will be left with R minus D by R. Or we can say that acceleration due to gravity at a depth will be G into 1 minus D by R. Okay. Now, if we consider the center of art, this point O, at center of art O, D will be equal to R, which means R minus D will be 0, or this term will be unity, which means GD will be G into 1 minus 1, that is 0. Which means that at the center of the earth there is no acceleration due to gravity. Now we know that weight of an object W is simply mass of the object multiplied by acceleration due to gravity. So if I say the center of the earth, weight at the center of the earth of an object of mass m will be this m into GD, which must be equal to, since GD is 0, which must be equal to 0. So an object at the center of the earth will be weightless. The object placed at the center of the earth will feel no weight. Now what we have found is that acceleration due to gravity at a height is given by this equation, and acceleration due to gravity at a depth under the inside the earth's surface is given by this equation. Now naturally a question arises that at what height above the earth's surface acceleration due to gravity is equal to acceleration due to gravity at a particular depth, which means that we want to find for what value of h and d, gd is equal to gh. So if I substitute these two values, what we get is that g into 1 minus d by r equal to g into 1 minus 2h by r. That is to say d equal to 2h. So if I go above the earth's surface and say that 100 meter above the earth's surface, if the acceleration due to gravity is something, then to have the same acceleration due to gravity, I have to go 200 meter below the earth's surface. Okay. Next factor affecting acceleration due to gravity, or the next cause of variation of acceleration due to gravity, is the very shape of the earth. Till now what we have done is that we have assumed that earth is a sphere, perfect sphere, and done the calculations. However, we know that is not the case. We know that the polar region, the earth is depressed a bit, right? The polar region is flatter, and then there is something which is known as the equatorial bulge of the earth, which means the equatorial part bulges out, somewhat like this. So if we find the radius of earth, we clearly see that the radius, the polar radius, let's call this RP, and the equatorial radius RE. Clearly the polar radius has to be smaller than equatorial radius, right? Now we also know that acceleration due to gravity g is equal to gm by r square, which means it is proportional to 1 by r square, right? So if I take gp by ge, that is acceleration due to gravity at polar region by acceleration due to gravity at equatorial region, then we will be left with gm by r p squared divided by gm by r e squared, which is equal to r e squared by r p squared, which must be greater than unity. Why? Because r e is greater than r p, so r e squared by r p squared must be greater than unity. That means that acceleration due to gravity at polar region must be greater than acceleration due to gravity at the equatorial region. Okay, now it has been found that the percentage variation, that is Gp minus Ge by Gp, if I multiply it by 100%, that is find the percentage of the difference of polar and equatorial acceleration due to gravity. This is found to be nearly equal to 0.5%. There is a 0.5% variation of acceleration due to gravity at polar region and at the equatorial region. Polar region, the acceleration due to gravity will be larger. Now we come to another important factor affecting the acceleration due to gravity, and that is the rotation of the Earth about its axis. We know that Earth rotates about its axis once in 24 hours, right? And due to this, at different latitudes, the acceleration due to gravity becomes different. Let us see how. And for that, we will consider a point at certain given latitude, say lambda angle. Okay. Now, if I consider this point will be traversing a circular path about its axis, Earth's axis, right? So this will have a circular path like this. Will be moving in a circular path like this. Okay. So if it's moving in a circular path, then that point will be subjected to centripetal force, right? It will experience certain amount of centripetal force, which will be radially outwards. So for this circular path, this is the radius. Let's say this is called r, small r. Okay, which means that there will be a centripetal force which will be acting along this. Force centrifugal, which must be equal to m r omega, right? Squared, mv squared by r or mr omega squared, where omega is the angular velocity of Earth's rotation, omega. Okay. Now, due to gravity, any object placed at this particular latitude will be pulled towards the center of the Earth. So mg will always act along this, radially inwards, right? So this will be our mg, force of gravitational attraction. Okay. However, this centrifugal force that is acting on it will have two components. One is radial component, the other one is the tangential component, right? The tangential, this being lambda, the tangential component will be sine lambda, and this will be Fc cos lambda. Okay. Now, if we consider this case, then what will happen? The net inward force at this particular point, which will be or mg lambda, the weight of an object, mass into acceleration due to gravity at that particular point, must be equal to mg, the net force of gravitational attraction, minus Fc cos lambda. Okay, which is equal to mg minus mr omega square cos lambda. Okay. Which will give us that g lambda equal to g, acceleration due to gravity, minus r omega square cos lambda. Now, if I look at the geometry of the case, this is the origin, this is point P and this is point C, say. So, in this triangle, what do we have? We have that this angle is equal to lambda, alternate angle, which means, and this length is the radius of the earth, right? So cos lambda, this angle, will be r by this, or we can say that r will be equal to r cos lambda, capital R cos lambda. So if we substitute the value of r in this equation, we get this is equal to g minus r omega square cos lambda 2 and cos lambda, so cos square lambda. So g lambda will be given by this. So at this latitude and latitude of angle lambda, the acceleration due to gravity will be this value. So for equator will be here, right? So the lambda will be equal to 0, implying cos lambda will be equal to 1. Therefore, acceleration due to gravity at equator must be equal to g minus r omega squared. Cos squared lambda is 1. At pole, what do we get at pole? Pole means at this, along the axis, right, of rotation, lambda will be equal to 90 degree, giving cos lambda equals to 0. Therefore, acceleration due to gravity at pole must be equal to acceleration due to gravity, the real value of it. Which means that acceleration due to gravity at pole minus acceleration due to gravity at equator. Variation of acceleration due to gravity due to latitude from equatorial level to the polar level, since will be equal to r into omega squared. So not only due to the shape of the earth, but due to the rotation of the earth also, the acceleration due to gravity at pole is greater compared with the acceleration due to gravity at equator, and which is by an amount equal to r into omega squared. Can you find the value for me?